We'll continue by solving more problems that rely on partial fractions. So this number 2 problem, another division problem. Now again, maybe you don't jump right to partial fractions. Maybe you try u as the denominator, and you get a 3x squared minus 6x minus 10, but it's just not quite going to work. Every once in a while you might be able to get something that it does cancel with the denominator, so we don't want to overlook that, but we tried and it didn't work. So I see, okay, I've got that division problem. It doesn't look that complicated. U as the denominator doesn't work. So I think about the decomposition. Decomposition, well, I have to factor the denominator. Well, first thing, I see a common x. And then I got the trinomial, and I could factor that into x minus 5, x plus 2. So, like I said, off on the side, I'll actually come down here now. And this is, you do need some room for this, because we can't just jump to the other piece. Again, if you're already setting up integrals with a and b, it just can really, really get messy. And it's not that you don't know how to solve it, it's just a little disorganization that you can't quite find something, you didn't finish a piece. There's a lot of little things that can come up. So I'm coming down here. There's the numerator over my factored denominator. The decomposition, I'll get an a over x, a b over x minus 5, and then a c over x plus 2. And just like we saw, that's just the decomposition. In order to solve this, I'm going to multiply everything by that common denominator so that this cancels. So I'm just left with the 9x squared minus 20x minus 20. On this side, the x would cancel here. So I'd have a, and I'd have both the x minus 5 and the x plus 2. Again, everybody, if you need to write it out, write it. It's x times x minus 5 times x plus 2. That's why everything canceled here. But here, just the x is canceled. These two are left, and the a. Plus, the b is left. The x minus 5 cancels, but that means the x and the x plus 2 are still left. And then here, the x plus 2 cancels, but the c, the x, and the x minus 5 are all still left. Just like the previous, I'm going to show you both techniques as far as solving for a, b, and c. But we all have to get here. If you like the clever x technique, that's still going to work very nicely here. I've got 3 factors. And like I said, maybe you're still not quite seeing the whole picture. So let me just start off. Let x equal 0. By letting x equal 0, well, I plug it in on the left side as well. Now we actually have x's on this side. So a 9 times 0 squared minus 20 times 0 minus 20 is all just 0 minus 0 minus 20. Equals, plug 0 in over here. I get minus 5 times 2 is negative 10 times a. Plug 0 in here. Well, b times 0 times 2 is all a 0. And similar here, c times 0 times minus 5 is another big 0. A equals 2. Just looking at that and solving, and we would get that a equals 2. Okay, so continue. 0 got rid of this factor, so therefore a was left behind. Now, next, I'll choose to let x equal 5. And looking ahead, 5 will get rid of all of this because that'll become a 0. 5 will get rid of all of this because that'll become a 0. And this will be left behind. Do have some messy work over here, though. Now when I plug in 5, well, plugging 0 in here was easy. But plugging in 5 squared is 25 times 9 is 225. Minus 20 times 5 is 100. Minus 20. So that looks like we're getting, what is that, 105. Let's just double check that one more time. We got 20. Yeah, so everything's all good there. And then like we said on the other side, this is a 0. This is a 0. But in between here, we have b times 5 times 7. So we got 35b. And again, just like up here, use the good clever X, eliminated 2 out of, well, really in this case, it's 3 out of the 4. We eliminated X, B, and C, only left with A. Here we eliminated X, A, and C, therefore we only had B. Finish solving this. B equals 3. And last, if we let X equal -2, that'll make that 0 and that 0, so C will be the only one left. But again, have to do the work over here. -2 squared is 4, times 9 is 36, -2 times -20, and then -20. So it looks like we got 56 here. On this side, 0 times whatever times A is again 0. B times -2 times 0. And then here, C times -2 times -7. So we get 14C. Finish solving here. C equals 4. So I still think this was tough getting to here. Solving for A, B, and C. This is not really, comparatively to some of the other things we've done in Calc 2, it's not the worst thing we've done. But again, it just might take some practice. Some people, this is really quick and easy. Other people just need a little more practice getting used to it. But now that we have the values for A, B, and C, again, maybe you did all of this on the side and you want to finish your problem down here. I'm just going to go back to the top because all these are simple fractions. So now I can rewrite this. My main integral, A is 2, so I've got 2 over x, plus B is 3, so I have 3 over x minus 5, plus C, which is 4, 4 over x plus 2. And again, take your time with it. This one is perfect, 2 log x. This one, 3 log x minus 5. 4 log x plus 2 plus C. There is your final answer. Any tests, you could certainly work the way I do. Just again, do me that favor, at least box your answer, maybe go back to the original, or at the very, very end of the problem, just identify answer. I don't mind bouncing around your work a little bit, just to be very clear at some point that you do have an answer and what that answer is. So that's what we've got right here. And, the little things we keep seeing, all these are pluses. So this could be bring in the 2, that's a squared. Bring in the 3, this is cubed. Bring in the 4, that's to the 4th power. This is one of those situations I was talking about. X plus 2 to the 4th power would always be positive. So that could eliminate the absolute value, but it's unnecessary. I mean, you could keep contracting this into a single log. This could eventually be log x squared times x minus 5 cubed times x plus 2 to the 4th. But that's not necessary. This is perfectly fine. But certainly be aware the book likes those contractions when you do get a bunch of logs that are separated by addition subtraction at the end. Okay, still several more problems I want us to do. And you might now start saying to yourself, well, I really like this clever X technique, but you'll see in the next couple, it's not so perfect. We started off with 2, that the clever X was so great, but still, before I move on, let me come back here, point out the systems of equations situation. That I've got the 9x squared minus 20x minus 20. Here, that is x squared minus 3x minus 10. So times A, I would get ax squared minus 3ax minus 10a. Literally just foiling, distributing all that. Similar here, I get plus bx squared plus That's a 2bx, right? bx times 2, just distributing up here. And similar here, cx times x, I get cx squared, and then I get a minus 5cx. Make this into a system of equations. Now we'll have 3 equations. There's 3 letters, A, B, and C, but it's really the powers of x. I'm going to get an equation from x squared, I'm going to get an equation from x, and I'm going to get an equation from the constant terms. The x squareds, how does this whole right side add up to the left side? Well, these 3 like terms, all these are x squareds. They have to combine to give me this one. So that would be 9 equals a plus b plus c. That's the first equation. Literally, 9x squared equals ax squared plus bx squared plus cx squared, but now the x's are unnecessary. That's the equation we want. Then from the x terms, the x to the first terms, those 3. So I get a minus 20 from the plain x term on this side. I get a minus 3a from here. We would get the plus 2b from here and the minus 5c from here. Last, the constant terms. Coincidence, right? Just that this coefficient was the same as this term, but hopefully we're seeing where everything's coming from. This constant term, there's only one constant term here. So that's where some people, they expect three equations and each one to have 3 variables. And then they start thinking, well, that definitely makes things a lot harder than the 2 equations, 2 variables we had on the previous page. But these are kinds of things that we're going to see. Nice little things that help us out in our problems. I'm just going to jump right here. And that gives me a is 2. And by plugging that in here, I now get 9 equals 2 plus b plus c. I could subtract the 2 to make that 7 equals b plus c. Here, I'd have minus 6 plus 2b minus 5c. But that minus 6 add to the other side. So I'd have a minus 14. And now you're back. And, we'll even see some nicer things that happen, but now you're back to that more common 2 systems, 2 equations, 2 variables, 2 equations. That's a more common basic system, and where you can, again, substitute, solve for one equation in terms of the other. So like here, subtract the c, b equals 7 minus c, replace this b with a quantity 7 minus c. You'll be able to eventually solve that for c, get c is 4. Come back here, well, if c is 4, plug that in, then b is 3. So it's still going to work. And again, the hardest cases, we're going to need a little combination of clever x and system of equation. So it's perfectly fine to have a preference and to try and have one as your more common go-to, but you really need to have at least a little experience with both. And let's see that. Let's just keep going here. So again, this looks really long, but realize all of this is just redoing what we did up here. So maybe it's still a lot of bookkeeping to keep track of. So again, like I said, keep your work neat, keep your work organized. But now let's move into another one. Let's now look at problem number, we'll call this one number 3. Integral minus 2x squared plus 4x plus 10 all over quantity x squared plus 1 quantity x plus 3. Denominator's already factored, but still, just take a moment before we just jump into partial fractions. I see that, that's certainly nice, but I even think about if I FOILed this out, I'd have an x cubed. I have proper setup, degree of the top is lower than degree of the bottom. I can quickly realize a u in the denominator is not going to work. So, okay, it's nice this is already factored. That helps me a little bit with the decomposition. And just like the previous one, I'm going to work on my decomposition down here, and then I'll come back up and solve the integral back up here. So I have minus 2x squared plus 4x plus 10. Again, this is already factored. I mean, I don't care the order. I'm just going to start with this one just because it's a little more basic. I'd have an a over x plus 3 on this side. And then that's it. It's just, they're only two factors. They're each to the first power. But just that this other factor is a quadratic, I need the bx plus c. So far, not a big deal. Nothing too different going on. Still, again, going to multiply everything by that common denominator. So the left side, I'm just left with the numerator. The right side, the x plus 3 would cancel, so I get a times x squared plus 1. Next, I've got that whole quantity bx plus c, and that would be times x plus 3. Do you realize there's a little issue here as far as the clever X technique is concerned? I can certainly start applying it, and this is what I mean, a nice little combination. If I let x equal -3, that'll make this factor go to 0, both b and c will be gone, and I'll be left with a. But just looking ahead a little bit, what value is going to make this 0? What value can I plug in for x that'll make a go to 0? We're not dealing with imaginary numbers, so it's a bit of a trick question. There is no way to do that. But this is still not a waste of my time, because this will still help. But again, just trying to point out, we're not going to be able to use the clever X technique the whole way in this problem. The previous two, they both work either way. This is going to need a little combination. So if I let x equal -3, yep, that's 0, so this whole thing is 0. So I get a, -3 squared is 9 plus 1 is 10. So I'm getting 10a is all that's left. Again, all this times 0, so that's just a big 0. Over here, +9 times -2 is -18. That's a -12 plus 10. -30 plus 10, I'm getting -20 equals 10a. A equals -2. Where do we go from here? Well, again, we can't use that clever X technique. So maybe just right off the bat, you already just distributed everything. We'll just connect the dots a little bit depending on how you started, but it's going to rely on us distributing all of this. So ax squared plus a. Over here, bx times x, I get bx squared. Bx times 3, I get 3bx. I get a cx, and I get a 3c. My system of equations. The x squared terms give me an equation. So -2 equals a plus b. The x terms, you don't have to underline like I'm doing. I just, especially for the first time some people are seeing this, they like that just to match everything up. These two pieces went with this. That's how I got the first equation. These two pieces, we've already seen it's not always two pieces, it could be 3, but just trying to make sure we don't miss anything. When you're setting up your system, if you goofed while multiplying out or while organizing, you're definitely not going to get the correct letters. The correct values for each letter, I should say. So x, I get a 4 on this side, and that's going to go with a 3b plus c on this side. And then my constant terms, the 10, well, I've got a constant term here, and I've got another constant term here. So if this is all you did, this is an even bigger pain to solve. 3 equations, 3 variables, but notice each equation actually only has 2. This one only has a and b. This one has b and c. This one has a and c. So you could play lots of substitution games, solve this for a in terms of b, so I could plug that in here, and then use 2 equations. So you can make this work by itself, But now let's embrace what we did earlier. If we did this and knew a equals -2, this becomes a piece of cake. Technically, I don't even need this middle line anymore, because if I plug -2 in for a here, add the 2, you get b is 0. Plug -2 in for a here, add the 2, 12 is 3c, and 4 equals c. That's what I've been trying to talk about. That's why I strongly encourage you to get a little practice with both, because sometimes this is a perfect example. This was a really quick and easy way to find a, but then it felt like we were stuck. And then if we just set this up, this could be a real pain. But by setting both up, not that we always want to blindly do that, but we want to realize what we prefer and when we're getting into a difficult situation. So if you preferred the clever X technique, you already got a good result. And then by setting this up and already having this result, this was super fast and easy to finish. If you started with this and you realized this was a more complicated setup, maybe you go backwards for a second to then realize, hey, I can at least get the answer for A and make this a whole lot easier. But now we put all of that together. And here's the other interesting thing, everybody. For this term, we had the possibility of both an x term and a constant term. That x term happened to be a 0x, so it doesn't have one. But if it had both, like if b was 1, you had 1x plus 4 over this. I'll say it again once we write this out. That's where you'd have to separate the fractions, right? That's where we'd have to do something like this and separate those two fractions. Lots of experience is helping us in these later sections. But all that, we've said a lot, make sure we finish. So what we have here, with this decomposition, everything we did down here, back to the beginning, this equals -2 over x plus 3 plus 4 over x squared plus 1 dx. All right, that's all there is to it. And you know, if you had these in the opposite order, this is where sometimes our letters don't match. I started with the x plus 3, but if you started here, maybe you had ax plus b over this plus c over this. Well, we have some slight variations here, but not much. But in the end, with your setup, so again, ax plus b plus c over this, you would end up with a equals 0. You would end up with b equals 4, and then you would end up with c equals -2. So just the order you put those factors doesn't matter, but that might be where somebody's work, we could have tiny little variations. So like checking any full answer keys, that could be a tiny little spot. Again, the work to get those values would be exactly the same. And now we finish, and that's where we get the reminder, not all of these are logs. Right? We've seen several of these. Well, this is a -2 log x plus 3, but this is not a log. That's for inverse tan x, and that is our final answer. Of course, plus c, that is the final answer for this integral. And just going backwards one more moment, pretend again, if b was 1 and c was 4, we would have had 1x plus 4 over this, and you would have separated it. 1x over x squared plus 1 plus 4 over x squared plus 1. This would have been a u sub. So again, they're not all simple. This was fairly easy. This was even easier. But again, a 4x over this, you do a little u sub to finish solving that one. Okay, last partial fractions example. Again, in your book, examples 2, 3, 5, all very, very good ones that are fully worked out. If you do want to get a little extra practice or have a couple that you could try on your own and see the full solutions before you jump into the homework. Let's get one more together. So this one is number 4. And for number 4, we will have, this is the integral 11x plus 12 over x cubed plus 4x squared. Now, some people might argue this one looks a little bit easier than number 3. Easy, difficult, that doesn't matter, everybody. They're all partial fraction problems that we, at a level we should be able to handle. So, again, of course, if you want to try u as the denominator, 3x squared minus 8x, no way that's going to cancel. So now we consider partial fractions, factoring. There's nothing to this one. Just factor out an x squared. It's just GCF. Not bad. As I keep doing, I'm going to come down here to work on my partial fraction decomposition. Don't be fooled with this one. Don't just write ax plus b over x squared. I mean, again, that kind of works, but you're making your life more difficult. A over x plus b over x squared, and then a c over x plus 4. Multiply everything by the common denominator, clear the fractions. 11x plus 12 on the left side. All of this, x would cancel, but I still have 1x left and the x plus 4 attached to the a, plus, now the whole x squared cancels, b times x plus 4. Here the x plus 4 cancels, so we just get a c times x squared. People, again, the clever x. I really believe most people prefer that, and I understand that would be my first choice as well. The clever x makes this so much easier than the systems of equations, but watch what happens here. I let x equal 0, and then we'll let x equal negative 4. When I let x be 0, I get 12 on this side, 0 plus 12. A times 0 times 4, well, that's 0. B times 0 plus 4, well, that's 4b. C times 0 squared, that's 0. Well, that's nice. That allowed me to find b very easily. Sorry, that's a b. And then if we let x equal negative 4, well, now I get negative 44 plus 12 on the left side. That is a 0, so a times negative 4 times 0, that's 0. Here, that's a 0, so 0 times b. But over here I get 16c. Do your arithmetic here. We've got negative 32 is 16c. So negative 2 would be c. Do you realize we're stuck? There's no way to eliminate b and c and then solve for a. So sometimes just the nature of these repeated fractions, that can be a little bit of a hiccup when it comes to the clever x technique. But we've already got values for b and c. That's certainly off to a good start. But I'm still, again, I'm going to do a little combination. The left side is done. But over here, that's ax squared plus 4ax, distributing here. I get bx plus 4b. And the cx squared is still there. The x squareds, there is no x squared here. You could write 0x squared if you prefer, or just use that result to get the first equation. The x terms, 11, would come from the combination of 4a plus b. And that last equation is pretty friendly. So, two things. If you started with the equations, well, bam, right away you get b. Once you get b, you plug in here, and then you can get a. And then once you have a, you could plug in here, and you can get c. So this, as a system, was not bad at all. Even though it looked a little ugly, we mentioned something like this earlier, 3 equations with 3 variables, but just the nature of the way this one came together, it's probably, I could argue that this way was actually easier in this problem because it's so quick. This gives me b is 3. Well, if b is 3, subtract that, 8 equals 4a, and 2 equals a. Well, if a equals 2, plug that in here. 0 equals 2 plus c. c equals negative 2. And now I've got my values for all 3. But again, if you combine, you already had b and c. Either of these were enough. You literally could have just gone right here and been done. You already had B, you already had C. That equation, use C as -2, and you get A as +2. We put all of this together. So I'm back up here. We've got the integral 2 over x plus 3 over x squared, and I'll kick that minus out in front, minus quantity 2 over x plus 4. And one more little place to be careful. That's a log, that's a log, that is not. That's a rewrite. That's 3x to the -1. So this first piece, 2 log absolute value x. Here the that's 3x to the -2, I'm sorry. And then when I take the anti, I get 3x to the -1 over -1 minus 2 log x plus 4 plus c. These could combine, again, the book loves to combine the logs. Bring that in as a square, bring that in as a square, log minus that log. So they would have log x squared divided by x plus 4 quantity squared. Maybe you clean that up, minus 3 over x. But as we keep seeing here, that's just fine. No reason to take that any further. That is a perfectly good answer. All right, so all of this covers the partial fractions, and that is without a doubt the major big part of this section. But then they also bring this up at the very, very end. And example 9 is a good one to follow here. This is a little bit about rationalizing. We saw in 7.3 those trig substitutions that we were working on. They can apply in some other places, but they were basic situations where we were trying to get rid of a radical. That when we had the radical x squared minus a squared minus x squared plus a squared, those trig substitutions allowed for identities that cleaned up that radical. I don't want to compare this too strongly, but that's at least the basic idea here. We are going to do clever U substitutions, and we are going to use those to evaluate. Number 1, we'll do cosine of the square root of x, and for number 2, we'll look at 1 over the square root of x plus 1. Now, this is not just always square roots. This could be cube roots as well. But when we're in this type of a situation, both of these, there's really nothing good to do, right? This first one, this is not an integration by parts problem. If anything, we'd think of this as a u sub. But if you start off with u as the square root of x, well, du is 1/2 x to the minus 1/2 dx. There's no extra x's to cancel. And this is where we'd often think, hey, nothing good, cross this off and try something else. But watch this, everybody. Here's the new little trick. That's a good choice for you. With all the things we've discussed before, prior, thinking about u as the inner part, that's not a bad idea at all. But here's the catch. We're going to manipulate u before we take the derivative. I'm going to solve this for x. So in this case, I'm going to square both sides. So I would have u squared equals x to the first. Now I will take the derivative. Now, we're much more accustomed to taking the derivative here, therefore u just becomes du. But this extra move, now we got to work on the left side. The derivative of u squared is 2u, and it gets marked du. And then the derivative of x is dx. In some ways, some people might say this is a little more similar to our trig substitutions, where we already had that exact piece to match. I don't want to compare it too strongly. It's more just, a clever u sub. Good choice for you, but instead of taking the derivative right away, make this little adjustment. Now when I plug this in, cosine of u, but now dx gets replaced with 2u du, and just a little rewrite, That's integration by parts. Is that better? Well, anything is better when we're stuck. And especially if we have good practice with integration by parts, that's almost that very, I don't want to say it's basic, because nothing's basic at this point. They're all difficult, but that's almost one of those more first common examples. But now here's the second issue. You made a U for a U sub, and now if you're going to set up integration by parts, U is a part of that formula. So I would at least suggest this. Just change the letter, everybody. I'd prefer to keep U and V for my integration by parts. So I'm just going to change that from a U substitution into a W substitution. Plenty of people would rather use the letter T. That's fine as well, of course. Any other letter is fine. But now in this form, that's more that straightforward integration by parts. U, the piece that gets easier with its derivative. dv, everything that's left behind but needs to be a piece that has a known antiderivative. I plug that all together, uv to w sine w minus the integral v du to sine w dw. This part is done. This integral, that's how I really know my integration by parts worked. The integration by parts didn't solve everything, but it took this minor multiplication issue. Now there's no multiplication. The anti of negative 2 sine would be positive 2 cosine. And I would still have to back sub. W was the square root of x, so 2 square root of x sine square root of x plus 2 cosine square root of x plus c. Nothing at all special about cosine if that was sine. If this was e to the square root of x, this would be the way. Just one more quick point before I move over to here. This is the problem we just solved, but just take a quick peek at one that's similar. Let's do sine, and let's do the cube root of x. Same basic situation. And no, I'm sorry, I should mention, this is why they call this U subs to help rationalize. We picked a U as a radical, but by doing this clever trick, we're guaranteed there's no radicals when we're done. So it's not that traditional rationalize like when we rationalize the denominator, but it still has that idea rationalize is just getting rid of the radical. So that is what this accomplishes. It gets rid of the radical, and by doing that, it kind of changed what we're looking at and allowed us to take a fresh shot at this problem, and this one required integration by parts. This would be similar. Here, I would have w would be the cube root of x, so I do w cubed equals x, 3w squared dw would be dx. This would become this integral. Same basic setup. Still that same multiplication. Just if you remember by integration by parts with a little practice, this will take 2 rounds of integration by parts. You let this be your u, but then you get a 6w. You went down by a power of 1, but it would take a second round to completely finish this. But my point is to come over here. It's not always just square roots. The trig subs, those very specifically went with square roots of all those forms. Square root x squared minus a squared minus x squared plus a squared. But those are all specific square roots. Here, it could be any other radical. The point is by making this move, the radical is gone. Okay, similar, but different when we come over here to number 2. I can still start with the same basic, and the derivative is not going to get me anywhere. And now, you don't realize this, but now I'm not worried about u. Not always will this type of rationalization lead to integration by parts. So let me start fresh. I'd still start with that u as the radical. And again, the du, just like we saw here, that's not going to help. But if I make u squared equal to x, 2u du equals dx. Now my integral has become 1 over u plus 1, but dx is 2u du. This has become, it's not exactly a partial fraction problem. This one's not even that complicated, but a little more similar. You put this on top, the degree is the same. So again, that's why we're not jumping to partial fractions, but it does have that fraction. You can do your straightforward polynomial division, or do that little trick I showed you. The trick works when the degree is the same here. I'm going to treat this 2u as u plus u, but I'm going to need a plus 1 for the first one and a plus 1 for the second one. So I'm going to have that balanced with a minus 2. So this over this is 1, plus this over this is another 1. It's slightly different. I could have algebraically tweaked that a little bit. Plus 2 minus 2, factor the 2 out and get that same result. So it's just the circumstances. Here we did that rationalization trick, ended up with a different looking integral, and it just happened to be one that we used integration by parts. Here we did a similar trick, similar technique to what we did here, but here when we plugged it in, we ended up with a fraction. So it's still going back to this rationalization is just getting rid of the radical. Like every other technique, it's just meant to simplify one piece to kind of help get the ball rolling, and then it's up to us to keep that momentum. So here, integration by parts, we finished it. Here, issue with fractions, I worked on it. Now I could finish 2u minus 2 log of u plus 1 and back sub 2 square root of x minus 2 log square root of x plus 1 plus c. There's a couple like this in the homework from this section. And then example 9 is another good one from the book. If you want to see a little bit more, try a little bit on your own, and again, have a nice fully written out problem to compare. Next section, 7.5. Again, we're going to develop general strategy. We've been talking a lot about it through each section, pointing out what's good, what's bad, what we hope for. But now we'll put all that together, and we're going to get a big worksheet with just a whole bunch of mixed integrals. We'll realize the techniques themselves, they all require practice, but even after you know how to use that technique, we have to be able to identify when those techniques would help us. So again, that's a lot of what we'll talk about in that next video, and that's what we're looking at for our next test.